In modern vehicles, the number of electronic control units, the ECUs, has grown exponentially. In advanced cars, we have something between 70 to 100 units on the vehicle. These ECU manage everything on the car, from basic functionalities like engine performance and braking to sophisticated features like driver assistance and infotainment. Each ECU communicates by sending and receiving signals, a small package of data that represents real-time information. An SDB acts as a central framework, organizing and defining the structure of the signals within the vehicle. It defines how the signals are identified, stored, and accessed, ensuring the communication between the ECUs. We can highlight four main features of an SDB: time series data management, real-time analytics, data compression, and scalability. Using the CanDB++2 from Vector, I'm going to show how a SDB looks like. If we start from top to down, we have the networks. For this example, I have only one network, powertrain. I have a few ECUs connected, and I have the complete list of frames. Frames are the package, and inside those packages, we have the signals that are transmitted. And we have also the complete list of signals. If we choose one frame, let's say FMR alarm BPC6, inside this frame we have this list of signals, and we can check how this frame is defined. So we have the name of the frame, the type, CAN standard, the ID, the transmitter, the transmission method, and the cycle time. We also have the signals that these frames contain, the transmitter, and the receiver. Now I'm going to start this application that's going to simulate communication on the powertrain bus. So we can select one frame and we can compare the information here on the real scenario with what is described on the SDB. Okay, and if we stop, we can select a frame, and we are going to select the same we chose on the SDB. And first, what we can check is the time difference, which means the frequency that the frame is sent on the bus. And we already have the information here, but if we select the two frames, we have the time difference. So here we have 100 milliseconds. That's the first difference between this interface and the SDB2. Here the time is defined in seconds, and on the SDB side is defined in milliseconds. And we also have the signals that are transmitted. And if we compare to what is on the SDB, we can check that is exactly the same signals. And another thing we can check is the frame ID. So on the SDB is defined as 86. And if we check on the real communication, we have the same ID, 86. So in summary, the SDB is organizing and defining the structure of the communication. Thank you for watching, and if you like this type of content, you can follow me in my different social networks.